This webcast continues the discussion of the lab on conservation of momentum, and now we are beginning part 2, in which we're going to look at some elastic collisions. This part of the lab uses a University of Colorado simulation, which can be found at the link in step 23. If you click on that, it will take you to the collision lab, and you want to click on Intro. Okay, we want to put checkboxes under velocity, kinetic energy, values, constant size, and more data. So this simulation involves two spherical masses, the turquoise on the left, which is number 1, and the pink on the right, which is number 2. These two spheres are going to move toward each other and collide, and the collision will be elastic. Oh, by the way, notice that by default, this elasticity is set to 100%. Please do not change that. We do want a fully elastic collision. And so when I click the play button, the two spheres move toward each other. Ooh, they bounced off of each other, and then they move. I'm going to let them move until they go out of this window. Okay, so they are moving, and I can see down here in this table at the bottom of the screen their velocities as they moved after the collision. Okay, so I'm going to return the balls. Okay, so when I look at it at the beginning, this velocity is the initial velocity, and then after I start the collision, this velocity is the post-collision velocity. If you notice, the velocity changed. Okay, so let's look at what we're doing here. So we are at step 27, which says that we're going to modify both mass 1 and mass 2 according to the values listed in the table. And we're going to leave the initial velocities of both objects alone. Leave them, let the velocities continue to be set at the default values. Okay, if you open up the Excel table, which was given to you as a template, you want to go to the Data Part 2 Elastic tab. Okay, and here in the first two columns, columns A and B, it gives me the masses that I should set up. It has already put in the default pre-collision velocities, and we're not changing those. And then it has calculated the momentum of each sphere as well as the kinetic energy of each sphere. Okay, so I'm going to go and set up the masses of both spheres to match the row in the table. So for the first row, both of them should be at half a kilogram. Okay, so I'm going to, mass 1 is already at half a kilogram, but I'm going to change mass 2, so it is also half a kilogram. I am not changing the pre-collision velocities. Okay, I just leave those alone. Then I will ask the balls to collide. I'll wait until they go off the screen. And then I can read the velocity here. Negative 0.5 for sphere 1 and 1 for sphere 2. Okay, so I'm going to go put those in. Negative 0.5 and 1 were the velocities of the two spheres after the collision. Okay, so I've entered those in my table. By the way, the table then calculates the momentum after the collision and the kinetic energy after the collision. Okay, so that's how I will get data. Then I'll go to the next data point where I leave mass 1 at half a kilogram, but I change mass 2 to 1.5. Okay, so I leave mass 1 at half, but I change mass 2 to 1.5 kilograms. I run the collision, and then I see that the post-collision velocities are negative 1.25 and 0.25. So negative 1.25 and 0.25. Okay. So I've taken 2 data points, and I would continue doing that until I get this table filled in. Let's go ahead to the next item though. It says show the detailed calculation of the initial pre-collision linear momentum. Okay, that's what I'm going to be calculating. That's in step 28. Okay, and it's of the system. Okay, so the momentum of the system at the beginning, so I'm going to put initial, should equal the sum of the momentum of the blue sphere at the beginning plus the momentum of the pink sphere at the beginning. And the momentum of each sphere is its mass. So for the blue one, it would be the mass of the blue sphere times the initial velocity of the blue sphere. And then for the pink sphere, it would be the mass of the pink sphere multiplied by the initial velocity of that pink sphere. Okay, so I can look at the first row of the table, and I can see that both of them initially had masses of 0.5 kilogram. The velocity of the first one was 1, and the velocity of the second one was -0.5. Okay, so 0.5 kilograms times 1 meter per second, that's for the blue sphere, and 0.5 kilograms times -0.5 meter per second for the pink sphere. So this is 0.5 kilogram meter per second, and this is, oh, it's a negative. Let me change that to a negative. It's a -0.25 kilogram meters per second, and so when I add those up, I get a total system linear momentum before the collision of 0.25 kilogram meter per second. Now I want to do the same thing, except this time I'm going to be finding the pre-collision kinetic energy. Okay, not the momentum, but the kinetic energy before the collision. Okay, so the kinetic energy of the system before the collision should equal the kinetic energy of the blue sphere before the collision plus the kinetic energy of the pink sphere before the collision. And kinetic energy is 1/2 mass times velocity squared. So this is the blue mass times the initial blue velocity squared, and this is the pink mass times the initial pink velocity squared. Okay, so I have 1/2 of 0.5 kilograms times 1 meter per second squared plus 1/2 of 0.5 kilograms times -0.5 meter per second squared. You know that negative sign will go away when I square that velocity. And so here I have, let's see, is this 0.5? No, it's 0.5 times 0.5. So that would be 0.25. And this is going to give me joules, right? It's going to be an energy. And over here, this is going to be 0.0625 joules. And so that gives me a total system kinetic energy before the collision of 0.3125 joules. Let me just go look at the table to confirm that it also found a system momentum of 0.25 and a system kinetic energy of 0.3125 before the collision, and it did. There's the momentum of the system before the collision, 0.25. And there's the initial kinetic energy before the collision of 0.3125. Okay, so I'm going to let you go and fill in all of the values in this table, and then you will paste it here at step 30.